I would like also to thank you very much, organizers, for inviting me the second time at this conference. At this time, I'm here in bone and flesh, so you can see me. Last time I was remote. So I'm going to have a lightweight talk comparing by Adina, so just some thoughts that you can use to maybe create some other thoughts, some other innovations. And I'm going to focus on this crossroads between different disciplines, physics with quantum mechanics, astrophysics, mathematics, and computer science in the evolution of the internet and the future of internet. So no phones, please. 5 seconds. Do you know who these guys are? Raise your hand. No phones, no phones. Okay. Okay, there are some people who know these guys. They are the Nobel Prize winners this year. Okay? I'm not going to tell you a lot about things because I think those of you who don't know about them, it would be nice to read about them. But, okay, now it's debatable after Adina's presentation. Jeff is considered the father of neural networks and also the father of AI. You've seen from Adina's presentation there are some other predecessors. He's a mix of computer scientist and also physicist. John Hopfield, it's a physicist. Actually applying neural networks and quantum mechanics to process images. And this is the first time actually that two quasi-physicists get the Nobel Prize winner for computer science. You know that actually the equivalent of Nobel Prize in computer science is the Turing Award. And we're going to have also a discussion about one of the recipients. So I've been a contrarian my whole life, and I'm a contrarian also with AI. I think we are at the beginning. I consider that AI needs tremendous improvement. It consumes too much energy. It needs too many data sets, millions, to make a very simple inference. And actually, it works with a lot of garbage. So these are the 3 aspects that I think need to be improved. And I think with all these investments, we're going to succeed to go to the next step. Then I'm going to go back to Adina's and Nade's comment about LLMs. Yes, we needed LLMs. We needed OpenAI. I don't use Google search anymore. I use Copilot. Google made a tremendous mistake by focusing on development software for advertising instead of improving the search engine, which is a complete mess. You do a search and you get hundreds of thousands of useless hits, most of them sponsored by people who pay money. So it's going to be a tremendous success of the new generation of search engines based on AI and LLM. Sorry, Google, you missed it. Okay, this other guy. Again, no phones. Fast. Who knows who this guy is? There's one guy here. His name is David Deutsch. He's a physicist. And he, in his youth, actually wanted to prove that parallel universe exists. And he used quantum mechanics. Well, by doing this, he invented the quantum computing. This is the father of quantum computing. Who knows about this guy? There's one guy, okay. So this is a great scientist. He's a mathematician, in fact, applying mathematics and computer science. He did tremendous research in real-time systems and what's the importance of time when you design operating systems. So time is one of the most exciting notion in our lives. So it's very difficult to describe it, and physicists spend years and years try to define it and understand it. Well, Leslie Lamport, I think by now it's Microsoft. I don't have his latest whereabouts. But He wrote some interesting essays. One of them it's that one. And what is the idea of this essay? The idea is the following. Software programmers are moving away from math and they're focusing more on the languages. They're becoming experts in languages. They're moving words left and right. So software programming has become, for many, the majority of software programmers, more like an art, like painting. And they forgot about algorithms, they forgot about math. So usually, programmers don't like very much math. And actually, Leslie is making the case that one of the reasons why we have all these cybersecurity problems is because, well, cybersecurity is about math, yeah? It's not about languages. It's a lot about math. And he's saying that because software programmers are not very well trained in math, they don't write software that is secure. And I agree with him, he's right. Look at this picture, yeah? What is this? I don't know, I didn't, maybe I didn't pick the right one, but it's a solar system, it's universe, planets, cosmic dust. But there is something that keeps all these things together. What is that? Gravitation. That's an essential notion. So let's go. This is a picture of some system that I designed with University of Waterloo for building a theoretical model of multi-cloud. Going back, going forth. They look the same, yeah? So what is the idea here? The idea is the following. Can we apply some of the laws of physics, gravitation, into designing better cloud computing systems? People talk about center of gravity when they describe databases. Can you imagine that a large database can be like a black hole? It attracts a lot of data. The other thing is also about connectivity. So how you can characterize a connectivity in internet and cloud computing, okay? So you have a certain bandwidth, you have two endpoints. Does it make sense to think that there is something equivalent to gravitation when we talk about these two concepts, connectivity and endpoints? I think it does. And together with the University of Waterloo, we built a theoretical model of multi-cloud that uses physics and laws from, not from quantum mechanics, but also from astrophysics to build this model. Okay, what is this? Whatever, a chemical plant or refinery. Before joining Institute for Atomic Physics, I had to work for 1 year in a factory. So I worked at the Lajan refinery. So I got to learn a little bit about this industrial plants. And I was actually amazed because this is a very complex system and still we can control it and make sense of it and generate a certain outcome. How do we do that? Well, the theory of automation and system theory. I don't know if you ever work in such a factory, but it's impressive to see such complex system being controlled by very simple mathematical models. Yeah? You have a system where actually you acquire some data, you have a model, you have a control loop, and then you succeed to modify the output based on your requirements. Just think about how difficult it is to manage a Kubernetes cluster. How damn difficult it is to use this. I actually am not a fan of Kubernetes. In fact, the history of Kubernetes is it started from a Google project which is called Borg, very old. Google, repackage it, call it Kubernetes, but it's a very complex and ugly system, difficult to use. Maybe we could use this kind of principles of theory of automation and systems theory to control the internet systems and cloud computing systems. Another food for thought. And these are the last slides where actually I think I look at the mirror. And because I spent some time also, I call this thing a trip to Tahiti because I'm a computer scientist. I'm not an expert. I was not an expert in solar systems, but I worked in some very successful solar companies. Then I learned about the energy grids and their design. So if you look at the design of the current energy grids, they are very static. So there is a need to keep the load and the demand in balance in order to have the frequency constant. And that's very difficult. Well, here comes the solar energy and renewables, which actually constitute a stress to all this old-fashioned energy grids, because the energy generated by these systems is unpredictable. So you need to force the old-fashioned energy grids to be dynamic, to maybe use concepts such as load balancing, auto-scaling, and other methodologies that we know very well how to use them in computer science, and we use them to design the internet and cloud computing. So I've been struggling for several years to convince the Department of Energy of the United States to use the internet model and cloud computing to design the new generation of energy grids, which are dynamic, where you have plug-and-play systems and still succeed to keep this important factor, which is called frequency constant. We're making progress on this project. I tried to convince also the Romanian Ministry of Energy to work with us in this domain. Hopefully I'm going to succeed in convincing them to do something. That's the last slide. Actually, it's interesting because I was ready to criticize one aspect. I'm talking about the third point, but again, Adina contradicted me. Most of the talk of computer engineers, if you compare them with the talk of a physicist or a mathematician, they don't talk about the past. They don't talk about the predecessors. They don't talk about the great minds that were before them. A physicist or a mathematician, when they talk about Einstein or Schrödinger or any other great mind in their domain, consider this an act of erudition. They are proud that they know the history of their topic. Very rarely you see in talks, especially, and I'm talking about a lot about the United States and a lot of conferences, especially from executives, talking about what was at the beginning on the topic they're trying to address. Adina actually contradicted me, and she started to talk about all this history, and I think which is the right approach. We always need to appreciate and promote the predecessors in our research. And another lesson actually that I learned in my career is there is always an influence of the past in the future. Many times we actually build a future looking into the past, because things are not falling from the sky. They are based from some ideas that actually somebody before us had it, and we just need to have the talent to make the associations between these ideas and create another piece of knowledge. And the last thought is one that was also mentioned by Adi and also a little bit by Adina. To build the next generation of internet, we need this melt, this aggregation of knowledge from many domains. And as I show you, we think about computer science, but in fact, computer science was created by the mathematicians, so it's really a branch of math. And then we see the influence of physics into this domain. So we need to do better into stimulating the aggregation of ideas from different domains of science. And I think with that we can build not just a better internet, but a better society. You can actually, if you want to contact me, I'm actually active on LinkedIn. Sometimes maybe too active. This is my private email address. Thank you very much.